All right, good morning. It's time to get started. All right, so as you probably realize, there's an exam tomorrow, 6:30, 12:10. If you guys could keep it down, it would be nice. The exam covers Chapter 5, Section 9 through 12. That's where we left off from Exam 2. All of Math Chapter E, as we covered in class, 6 and 7. Nothing from Chapter 8. The one thing that will be on there that doesn't show up explicitly in the textbook yet is this concept of natural variables. And then questions 1 to 10 on homework 12 are relevant. All right, the other thing I wanted to let everybody know is that the review sessions, how many people went to review sessions? All right, Melissa, you did too, right? Yeah, yes, you did. All right, just making sure everybody's honest. So the review sessions were captured and they're posted on Canvas. All right, so for today we have a little bit of stuff to finish up in prep for the exam tomorrow, and then I'm going to cover a little bit from Chapter 8, and then we're going to stop a little early because it's Monday, and what would Monday be without a quiz, right? And the quiz will be extensive, and it's designed to help you think about things for tomorrow's exam, all right? Okay, so things that we've covered previously. We've shown that we can use calorimetry to determine absolute values of entropy, right? And that's because we know that ds is Cp over T, or the heat capacity at constant volume over T dt. So that means I can integrate that and determine absolute values of entropy. We also saw that we can use this to calculate delta S for a reaction at a temperature that we don't know delta S of the reaction for, all right? Okay, also last time we showed that for a phase transition, it's a reversible process, it's isothermal, and we showed that that means that delta S of the phase transition is the heat transfer over the temperature of the phase transition. And if I say that we're going to do it at constant pressure, that heat transfer is the same as the change in enthalpy. We saw that the third law of thermodynamics, one way that we can say it, is that the entropy of a perfect crystal is 0 at 0 Kelvin, and that allows us to determine the entropy from a calorimetry experiment. All right. We also mentioned that as temperature approaches 0, the heat capacity of our solid approaches 0. We've defined standard molar entropy, entropy per mole of a substance at 1 bar, and whatever temperature we've defined as our standard state. Right. From there, we talked about qualitative changes in entropy or qualitative differences in entropy. So the easy one to visualize is if I have a solid, liquid, or gas, same substance, I expect that the entropy of the solid phase will be less than that of the liquid, which is less of that of the gas phase. So we can discuss that in terms of randomness or disorder. We also saw that as the mass of a molecule goes up, or as the number of atoms increase, in both those cases, what we see is that the entropy is going to be increased for more massive and greater numbers of atoms in our molecule, right? And then if I have an isomer, then we look at what motions are available to the molecule, and what we see is that the more compact the structure, the cyclic structures have lower entropies than long chains do, right? We talked about chemical reactions and delta S of a chemical reaction. So as we expect, if we go from the solid phase into the liquid or the vapor phase, we see an increase in the entropy. If we start in the solid or liquid and end up in gas, that's going to be an increase in entropy. And if it's a completely gas phase reaction, it's going to be dominated by the change in the number of moles of gas. All right? And then where we ended last time was talking about calculation of the entropy of a reaction at a temperature that's different than what we know the entropy of reaction for. So in this case, we know the entropy change for the reaction at T1, and that allows us to calculate at T2 by looking at Cp over T between the two temperatures for both the products and the reactants, right? Okay, so what we're going to do today is we're going to talk a little bit further about the calculated or spectroscopic entropy, which we've previously said corresponds to what we get from the partition function, versus the heat capacity or what the textbook indicates as the experimental. And what we see is that we sometimes see a difference between those two. We always see, if there is a difference, that the calculated value from partition functions is greater than that experiment of the calorimetric, right? We call the difference between those the residual entropy, and we'll talk a little bit more about what causes that in a little bit. From there, this is just directly out of Gen Chem 2. If I have tabulated standard molar entropies, I can calculate the delta S of the reaction by looking at the products entropies versus the reactants. From there, we'll go into Chapter 8, talking about Gibbs energy, which you guys have previously seen. How many people have heard of Helmholtz energy before? A few of you have. So the Gibbs energy works as a predictor of spontaneity for constant temperature and pressure processes. So I need something, or we need something, that talks about whether something's spontaneous or not at constant volume and constant temperature, and that's the Helmholtz energy. Okay? All right, so picking up where we were last time, we had just talked about the fact that we can have an imperfect crystal if we're doing a calorimetry experiment. And I left something out of this equation, so I need to fix that. Basically, what we've said is that if I have an imperfect crystal, the entropy at 0 degrees Kelvin of a real crystal can be related to NKB natural log of Z, where Z is the number of random orientations that are equivalent for our molecule. And the example that I've selected to look at was CO. So CO has a really low dipole moment, which means that energetically there's no reason for it to align CO, 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 CO. All right? And so as we cool it down, the carbon monoxide, get it into the solid state, it tends to just randomly align either CO or OC. So that says that experimentally, my solid carbon monoxide crystal is going to have a random arrangement of these atoms, or these molecules, right? And there's two different possibilities for that. And so what we can say is that at 0 degrees Kelvin, for the calorimetric entropy, that S0 will be given by NKB ln, and in this particular case, 2, because there's two orientations. All right? Now, if I was talking about, say, ammonia, NH3, and if I replaced one of those H's with something else, right? So, and it doesn't matter what it was, so I'd make it NH2X, right? Then there would be 3 equivalent positions, and my answer would be S at 0 degrees Kelvin is NKB ln 3. Does that make sense? Okay? All right, so in general, we can say that the entropy from a calorimetric experiment needs to be corrected by including this factor. Okay? We all good? All right? And this explains why the calorimetric one is always larger, because we don't really have a good way to measure this, right? We can measure all the rest of this, but we can't measure that S at 0 directly. Okay? All right, section 7.9 basically is that we can use S naught, so they may be used to calculate delta S naught of a chemical reaction. Okay? All right, so it's sort of the same thing that we did with formation enthalpies to calculate delta H of chemical reactions. All right. There is one big difference, right? If we think about what we did with enthalpies, we said we broke that reaction into 2 hypothetical steps. We took the reactants, converted them to elements in their standard state, and then we took the elements in their standard state and converted them to products, right? So that means our reference point was the elements in their standard state. In this case, we don't need a reference point because we know we have absolute values of entropy, right? 0 degrees Kelvin, perfect crystal, that's the 0 point. right? And so if we go to tables of thermodynamic data, we look at N2 and H2, delta H of formation for those will be equal to, help me out, if they're in the gas phase, is equal to 0, right? Because these are reference to the formation reaction. This is the absolute value of the entropy of nitrogen at this temperature, at this pressure, okay? All right, and so as long as we know that, then we can say that delta S of the reaction is really going to be given by the molar entropy of our products times the number of moles of product summed over all of the products, right? That's our final state, so that's S of our products. And then we reference that, or we compare it with our initial state, which will be M S bar naught of our reactants. And again, we have to sum over all of the reactants, all right? So this really is S of reactants, and this term is S of products. All right, so we don't have to do any hypothetical steps, all right? So this example, delta S, we want to know the enthalpy or the entropy change for this reaction. All right, again, this means at 1 bar, and this is what the temperature that's referenced in this case. In this particular case, it's at room temperature around 298 Kelvin. We've talked about this qualitatively. What do you expect the sign of delta S to be for this reaction? Positive or negative? It's going to be negative because I've reduced the number of moles of gas, right? Okay, and we can see that through the calculation. So in this case, I look at my products. I have 2 moles of NH3, so I have to multiply that by 193 joules per K per mole. All right, so that's the entropy of the products, and then minus that of my reactants. So I've got 1 mole of nitrogen, 1 mole N2, so that's times 192 joules per K per mole. And my other reactant, I have 3 moles of hydrogen, and I multiply that by 131 joules per K per mole. All right? And this comes out to be equal to minus 199 joules per K. Right? As we expect, it's negative. Okay? All right, so this reflects everything that's you're responsible for the exam. All right? So what I want to do now is I want to take a moment to do a little bit of a preface to Chapter 8. Okay? All right, so what we've previously shown is in order to determine whether a process is spontaneous or not, I need to know what delta S of the universe is. Right? So we can say spontaneous processes delta S of the universe is greater than 0. Okay? All right. And we know that delta S of the universe is going to be delta S of the system plus that of the surroundings. So I can say delta S of the system plus delta S of the surroundings needs to be greater than 0. All right? We've just shown that if we're talking about a chemical reaction, it's pretty straightforward to determine what delta S of that reaction is. So it's easy to know what's going on with your system. We've also seen that it's complicated when we start thinking about the surroundings. All right? And so what we'd like to do is to take this equation and derive an expression that depends only on system parameters, because that's what we easily can get at. Does that make sense? Right? And so what that really means is that we need to focus on delta S of the surroundings. Right? So I can say that delta S of the surroundings is going to be equal to, so I have dq reversible of the surroundings over T integrated. All right? That's just straight up from our definition of entropy. right? Okay, so if we think about the surroundings as being the universe as a whole, right? If I light a match in this room, is that going to change the temperature of the universe as a whole? Not measurably, all right? And so if our universe is large, we can basically say this is 1 over T. It's a constant. It comes out front, okay? All right. And then I look at this dq reversible surroundings. Well, that's going to be the heat transfer with respect to the system, but the opposite direction, right? So that's going to be equal to the integral minus dq reversible of the system, right? And because this is just the integral of a differential, and it's an inexact differential, that means it's going to be equal to q, right? So that becomes minus q reversible for our system over the temperature, okay? All right, so now I've got everything in terms of my system, so I can plug that in for delta S of the surroundings. So this becomes delta S of the system minus Q reversible of the system over the temperature is going to be greater than 0. Okay? All right, you can already see this is getting close to what you remember from, from Gibbs energy, right? So what I can do at this point is I can multiply both sides of this equation by minus T. Okay? All right, so that's going to get me, is that what I want? Delta H, yeah. So that's going to get me minus T delta S of the system plus Q reversible of the system. All right? Now, because I've multiplied both sides by a negative number, what happens to the greater than sign? It flips. It becomes less than 0. Okay? All right, so now this basically says I can predict spontaneity by knowing what the heat transfer is and knowing what the entropy is with respect to my system. All right? And we've seen that there's two different experimental conditions that we choose to give labels to. So at constant pressure, QP is the same as delta H, right? So that basically means I'm going to plug in delta H for this, and what I end up with is delta H minus T delta S is less than 0, all right? And what does that correspond to on the left side? That's a change in the Gibbs energy, right? That's delta G. Okay, does that make sense? All right, so keeping in mind, again, this came from our second law, delta S of the universe has to increase for it to be spontaneous. Once I define constant pressure and get everything in terms of the system parameters, system observables, then I have delta H of the system minus T delta S. It's got to be less than 0. Okay? All right, and the only thing I'm not going to write, I'm just going to state this, right? So QP, I've selected this to be the reversible path, but we know that delta H is a state function. So it doesn't matter whether I choose a reversible path or not, right? Okay, so that takes care of constant pressure processes. And then if I think about constant volume, right? In that case, I have Q sub V, right? And if we are limiting our discussion to pressure volume work, we know that delta U is equal to Q plus W, right? And if it's constant volume, that tells me W is equal to 0. So Q sub V is the same as delta U. All right, and then I can plug that in and I say delta U minus T delta S will be my criteria for spontaneity, and this is delta A, Helmholtz energy. Okay, does that make sense? All right, moving into chapter 8. We're going to be talking about Gibbs, G, and Helmholtz energies. All right, and some people might say, why is it labeled A? Does anybody know why it's labeled A? This A stands for Arbeit. Anybody speak German? Know any German? It's work, all right? So it comes from the German word for work, okay? All right, so setting the stage. We've previously said ds greater than or equal to 0 for spontaneity and equilibrium. And that referred only to an isolated system. So we want to have some parameters that are dependent only on our system, right? And we need to think about something that relates to delta S of the universe. And we've already shown that that's going to be the Gibbs energy and the Helmholtz energy, right? So for constant pressure and temperature, dg less than 0 is going to be our criteria for spontaneity. And for constant volume, dA is less than 0. Okay? All right, so now what we want to do is a little bit more of a rigorous derivation of why we have dg and dA as our criteria. So we can start with section 1. At constant T and V, the sign of ds, or dA, sorry, determines spontaneity. Okay? All right, so what we can do is we can start with the first law. du is equal to dq plus dw, and we know that if we limit ourselves to pressure volume work, dw is going to be minus pdv, right? And we also know from the definition of entropy, ds is equal to dq reversible over t, that we can say that dq is the same as tds. Okay? All right, so du is equal to dq because this is equal to 0, and dq is equal to tds. So du, dq, and tds all related. And from the second law, we know that dq is going to be less than or equal to tds. Okay? And then I can say du is less than or equal to tds. All right? What I can do is I can rearrange this equation, all right? And I can say that du minus tds is going to be less than or equal to 0. Okay? All right, so I've just rearranged this. All right? Okay, and then I step back and I say, well, I can define this new function, u minus ts, all right? And that's going to be less than or equal to 0 as long as I'm holding the temperature constant. All right, so we define A to be u minus ts, right? And therefore we can say, whoops, then we can say dA less than or equal to 0, all right? So dA is less than 0 for spontaneous process as long as we have constant temperature, and volume. And it's going to be an equality whenever we have constant temperature and volume. Okay? Does that make sense? All right. So the timer went off. That's to tell me that it's time to give you the gift of the day. All right? You can work in groups. We're going to do A through C as a class, and then the rest of it you're going to do on your own in your groups, and hopefully you'll get some good discussion. Again, most of this is primarily designed to help you prepare for the exam tomorrow in thinking about entropy. Did you guys get one? Do you want another one?
Yeah, that's right.
Okay. Whoops. All right, so I wanted to take a moment to talk a little bit about what this problem's saying. So I have this isolated system. So that really means that it's our universe, right? And that consists of a very, very large thermal reservoir at a particular temperature, right? So the reason that we say that it's a large reservoir at 283 Kelvin is because this is saying I don't expect the temperature of this huge, vast thing to change. Okay? All right. Inside of this reservoir, I have some ice present at 283 Kelvin. Now we expect at a pressure of 1 bar that that ice is going to melt, right? So that's the spontaneous direction of the process. Does that make sense? All right, and what we're going to do is we're going to calculate explicitly what the entropy changes are for the reservoir and for the ice itself, okay? And the sum of those two we expect to be, help me out, do you expect it to be equal to 0, greater than 0, or less than 0? Delta S for this little universe is going to be, it's going to be greater than 0, right? Because we know it's not at equilibrium. The system's isolated, okay? All right, so the very first part of this, we're basically saying, here's delta H for melting of ice at 273. So that's the normal temperature at which we have the phase transition at 1 bar, right? And what I want is delta S for that, right? So reminder of things that we've previously shown. Delta S, this will be a fusion. And I'm going to take this a little bit tediously, right? I'm going to start by saying, well, that'll be the integral of dq reversible for our phase transition, which is fusion, over the temperature, right? And this is where we step back and we say, all right, the thing I know is that if I'm at the melting point, I don't see a temperature change going from liquid to solid or solid to liquid, right? And if I infinitesimally raise the temperature, all goes into one phase. Infinitesimally reverse the temperature change, I go into the other phase. So this tells me that it is reversible, right? And it also tells me that it's isothermal, right? And so that means I can pull the temperature out front. So it's going to be the temperature of fusion, right, which we know is 273 Kelvin. And then I've got the integral of dq. Well, that's just going to give me q reversible. And that will, if I'm doing this at constant pressure, that's going to be the same as delta H of fusion over the temperature of fusion, all right? Okay, so at this point, I can say that's going to be 6,004 joules per mole. And divided by the temperature, which is 273 Kelvin, and that gets me, there I've got to look at my key, plus 21.99 joules per Kelvin. Okay? All right. And then let's, before we go forward, yeah?
Joules per mole?
Yes. Yeah, okay. This is joules per mole. We're going to multiply this by the number of moles to fix that. Thank you. No. Thank you. All right, because we're talking about 1 mole. Okay, so qualitatively, let's talk a little bit about this. I'm going from solid to liquid. We see an increase in entropy. That's what we expect, right? Okay, so in the next section, if we're talking about being at 283, this ice at 283, we know that's not stable. That's a metastable state or superheated ice. All right? I'm giving you delta H for the melting of ice at 283. On the other side of this, you're going to calculate that. You're going to show where that comes from. All right? So we've said the thermal reservoir is large. All right? And what we want to do now is calculate what delta S is for the reservoir. All right? All right, so delta S of the reservoir, we're going to say RES. All right? Again, starting at basics, that's going to be the integral dq reversible for the reservoir over the temperature. Okay? Now, because we know that this reservoir is huge, its temperature's not going to change. All right? So that means it's going to be equal to 1 over T. Right? And we know that temperature is 283. Okay? And then the next thing that we know is that this, in the numerator, I've got Q reversible for the reservoir. All right? Now, in terms of what's happening inside of this, in order for me to melt that mole of ice, I need to absorb 6,400 joules. Right? And that comes from the reservoir. Right? So that's going to be equal to minus Q reversible for the fusion process, right, over the temperature. Okay? All right, so at this point I can plug my numbers in. That's going to correspond to minus 6390 joules divided by 283 Kelvin. All right, and times 1 mole, because I have 1 mole of ice in there, right? And that comes out to be minus 2258 joules per K. Okay? All right, so this is the delta S that's occurring with respect to the reservoir itself. And it's negative, right? Because we know that it's losing heat in converting the ice into water. Okay? All right, so the next thing that we can do is say, all right, this is delta S for the reservoir. What's delta S for the water itself, for the ice that's being converted? All right? All right, so in this case, we want delta S at 283 of fusion. What we've done up above is we've determined delta S at 273. Right? And so that means I need to know delta S for my reactants and products between 273 and 283. Right? So that's going to be the integral (283) to 273 of the number of moles times the heat capacity per mole at constant pressure over the temperature, dt, right? And this is specifically going to be about the solid. And then, so this is basically saying I'm taking solid at 283, I'm changing it to 273, and then I'm going to let the ice melt. So then I have delta S of fusion at 273. And then to make it completed, I need to integrate from 273 to 283. Now my liquid. And that'll be NCP of the liquid over T dt. Okay? All right, so the heat capacities that I've supplied to you are approximations. How do you know they're approximations? They're independent of t, all right? So if I wanted something exact, I'd need to use t plus t squared plus t cubed, right? As you guys have done on a previous homework assignment, okay? But that makes the integral easy for us to do, right? So that pulls out NCP S, right? And then I've got the integral of dt over t. What's that going to give me? ln t2 over t1 plus delta s plus, and then my next integral will be NCP of the liquid phase ln t2 t1 for the final step of this, right? So at this point I can plug numbers in. So it's going to be 1 mole of my substance. The molar heat capacity for the solid is 36.8 joules per mole per K. And then I have the ln of 273 over 283, right? We know delta S from our calculation is 21.99 joules per K. And then my final term will be 1 mole times 75.3 joules per mole per K times the natural log of 283 over 273. Okay? All right, this comes out to be a positive number. This comes out to be a negative number, and that should make sense. I'm cooling this. Here I'm heating it. Okay? And putting it all together, we end up with plus 23.38 joules per K. All right? Okay, so now I'm going to let you guys loose. The balance of it is for you to work on. Melissa or I will be happy to answer questions. So I want you to tell me what the total entropy change is as delta S of the universe for this isolated system, and then the stuff on the reverse side. And of course, as usual, the key will be posted whenever I post the annotated lecture notes.